All right, so if we're going to name compounds and write formula, hopefully this is going to be mostly review for you, okay, that it's something you learned in Science 9. But we're going to review it here. We're going to talk about the difference between ionic and molecular compounds, okay, because we got to know which is which. If we are, right, one has a metal in it, the other doesn't, okay, being able to tell them apart so that we know which naming rules to apply, okay, how to figure out how many of each atom are going to be in a compound, okay, and things like that. We got to be able to write compounds correctly, because if we can't do that, we'll never get reactions written correctly. Okay? In chemical reactions, we got to make sure we got the same number of each kind of atom on both sides. And if I don't write the formula right on one side, I'm never going to make it balance on the other. Okay? It ends up being very, very important. It's one of those kind of fundamental skills in chemistry that we have to have, is being able to write proper formulas, read the names properly, write the names properly. All right, so we got to be able to identify a compound as ionic or molecular, and we got to be able to write the formula in proper names. Okay, so ions and ionic compounds. In an ionic compound, there's going to be always a metal and a non-metal. Okay, so if you're looking at a compound and it's got a metal in it, it is ionic. Okay, like a binary compound, a simple one. Okay. So there's a metal. Metals are always on the left side of the periodic table, okay, and a non-metal, which are always on the right side. What divides left from right? Okay, the metalloids. I'm thinking of one kind of. Yeah, there's some. I was thinking of more of a really defining line. You guys never been told what this thing's called? This is the staircase. Yeah, the staircase here divides the metals, left side, from the non-metals, right side. More metals than non-metals. Okay, there's way more metals than there are non-metals. All right, so all the non-metals are to the right of the staircase, and the staircase is always indicated, okay, on a periodic table as a bold line. Right, it's always thicker than all the others. Okay, the metalloids are always right up against it. So the metals that are right up against the staircase behave in kind of a transitional way between metals and non-metals, which is why we don't often see them in compounds that we deal with, because they're weird, for lack of a better term. Okay. All right, so in these molecules, so when a metal and a non-metal combine with each other, something happens with the electrons. Okay, and that is that they're traded. Okay, that's the weird thing about ionic compounds, is the electrons get traded. The metals give them away. The non-metals take them. Okay, the reason for this has to do with the orbitals that we talked about the other day. Okay, so if we're looking at sodium and chlorine here, just as an example, right? So if I look at a sodium atom, okay, I'm just going to represent the nucleus with one big circle here. Okay, sodium has 11 protons, okay, and it has 12 neutrons. Okay, so I'm just going to write in here, protons equals 11, neutrons equals 12. Okay, and then it's got how many electrons? 11. Okay, now the way that Bohr diagrammed this, and actually Bohr was right about the energy levels, he just wasn't right about the shapes. Okay, he said the first orbital can hold 2 electrons because it's small. The electrons don't want to be close together because they repel each other. Okay, the next orbital out can hold 8 electrons. Okay, so they fill up like this. Once the 4 kind of ideal positions are taken, then they actually pair up, which is weird because they're supposed to repel each other, but yeah, okay? This isn't really what it looks like, but it's the way we diagram it. All right, so we're up to 10 electrons. We're supposed to have 11, so we need 1 more orbital. Okay, so the last orbital contains 1 lonely electron. Okay, all atoms want to have their outer shell full. Okay, for whatever reason, that's like the meaning of life for atoms. They want to have this full outer shell of electrons. That shell that has only 1 electron in it can hold 8. So which is easier? Sodium has to go out and look for 7 more electrons, or find someone who wants 1. Find someone that wants 1. It's way easier to dump 1 than look for 7 more. Okay, so this is typically the situation that metals are in. Their outer shells are less than half full. So it's easier for them to dump the electrons they have than look for other ones to fill their shell with. Okay, non-metals are in the opposite situation. Their shells are more than half full. right? And so as a result, it's easier for them to pick up a few to get full than to find owners for the ones they already have. Okay, everyone kind of follow there? So that's what we're looking for. Question? Right. Yes, if it loses that electron, then it's happy because its outer shell is full. However, now it has one less electron than it has protons. So now it's no longer a normal atom. It's now what we call an ion. Ions are charged particles. Okay, this now would have a charge of +1 because it has one more proton than it has electrons. Okay, and that's why you can see up here on this diagram it says Na+1. Right? And sodium would have a +1 charge as part of an ionic compound. Now with chlorine, okay, so if we look at chlorine, chlorine has 17 protons, okay, and it's got 18 neutrons, right? So if I'm looking at a chlorine atom, okay, and I draw its nucleus, so P equals 17, N equals 18, okay, and then we're going to look at how many electrons it's got to have. 17, okay, so 2 in the first one. Okay, now we're up to 10. This next shell, which is the same shell that sodium had, but its shell is going to have 7 in it. Well, it's a match made in heaven. Okay, sodium needs to dump 1 electron. Chlorine needs 1 electron. Okay, that's why sodium chloride is a very common substance. Okay, they go together very well. All right, so in an ionic compound where there's an ionic bond, the electrons are traded. Okay, so sodium gives this electron up, okay, and loses its outer shell. Well, sort of. Now its new outer, its outer shell is now full. Okay, and its electron ends up over here, and chlorine's outer shell is full. Everybody all right with that? Okay, so it seems like it works out pretty well for everybody. The thing about ionic compounds, though, and ionic bonds is they're not very strong. Don't take this in a sociological perspective, but both people got what they wanted here. There's not really any reason for them to remain together because they both kind of got what they want. Again, don't take a sociological perspective on this, but that's how these ionic compounds work. Ionic bonds are not very strong, okay? Which is, again, why, or is one of the reasons why ionic compounds are very soluble in water. Put them in water, they just dissolve really easily. Well, what happens is the compounds just break apart, and now these charged particles are floating around inside the solution. Okay, there's chlorine atoms, or chlorine ions, sorry, that have a charge of -1. They have an extra electron. Okay, and sodium ions that are floating around that have a charge of +1. Okay, so ionic bonds form, but they're very weak. Okay, because again, they've both gotten what they wanted, a full outer shell of electrons. Okay, and that's again why we see metals and non-metals always going together. Okay, non-metals can't go together and make this happen because they all want electrons. Okay, no one's going to give them up. They all want to get more. Okay, and metals don't go together because none of them have enough electrons for them to go together. Okay, all right. That sort of makes sense there? Okay. It is an alloy. It's just a mixture. They're not chemically bonded together. So yeah, alloys are strange. Okay, that's a good question. Alloys are not a new compound. They are just that, a mixture. If I pour these two metals together as liquids, when they cool, they'll solidify and make what's called an alloy. But again, it's just a mixture of the two, right? You can separate an alloy, you make it hot enough, they'll separate again, right? Okay, so for naming these binary ionic compounds, okay, we name the metal first and then the non-metal, okay? The only thing that we do that's kind of strange is we take the name of the metal, state it in full, and then we take the non-metal and change its ending to "ide." Okay, so instead of saying sodium chlorine, it's sodium chloride. Okay, it indicates that these two things are bonded together. Okay. All right, so some of the examples we have here: magnesium oxide, sodium fluoride, aluminum sulfide. Okay, always ends. If it's a binary ionic compound between two elements, it's going to end in "ide." All right, so really that's all we need to remember here. Okay, when we're naming them, name of the metal, stated in full, name of the non-metal as an "ide" suffix. Okay. Question there? Okay, we got to remember to name both ions. Okay, some people, they get kind of in a hurry or whatever, and they don't name the whole thing. Instead of writing sodium chloride, they write sodium, and then they forget to keep going. I don't know why, but I see that happen all the time. Okay, and here's this. This is the thing that gets everybody. The name of a chemical compound is not a proper name like Jane Doe. Okay, that's a proper name, so the names are capitalized. Sodium chloride is not a proper name, it's a chemical designation. As a result, it's not capitalized unless you're starting a sentence with it, which right now off the top of my head I can't do. Sodium chloride is table salt. Okay, there you go. I would capitalize sodium there, okay, in that situation, but never in any other situation. It's not a proper name, so they're not capitalized, but it's a terrible habit, and we all do it. We have to break it because we don't use the common names. Salt is actually a term that applies to all ionic compounds because all ionic compounds are crystalline solids or salts at room temperature. Okay, so yeah, we don't want to use common names. I mean, if you know a common name for something, we don't write it. We want to use the proper technical term for it. Okay. No, we don't write the charge or anything because we don't need to actually, and we'll get to that. The name itself, when these two things go together, because of their charges, there's only one way they can go together, so we don't have to indicate it. Okay. The only time we would indicate a charge in a name is when we have a metal that has more than one possible charge, and then we have to say which one it is. We're not there yet. We will be, but we're not there yet. What's that? Yes, ionic compounds, all compounds actually, end up having a charge of 0. Okay, so aluminum plus chlorine, okay, Al plus Cl2, chlorine's special, it comes as pair, okay, aluminum chloride is what it produces, okay, no capital letters here, okay, and that's AlCl3. We'll get to why we know it's a 3 here in a minute, okay, and how we balance that comes much, much later. All right, so charges are positive on metals, okay, and negative on nonmetals. True compounds always have a net charge of 0. Okay, if they don't have a charge of 0, they're not a compound, they're an ion, and that's a different thing. Okay, so looking at our ionic compounds here. First one, obviously, pretty straightforward because we've already done it. Okay, the metal here is sodium, non-metal is chlorine, so this stuff's going to be sodium chloride. That is a lowercase s. I know it doesn't really look like it, but I didn't capitalize it. Okay, sodium chloride. Now you know why I typed the notes out previous. My penmanship is horrible. Okay. My grade 6 teacher, she told me, your penmanship is terrible. You really need to work on that. Now you gotta remember, grade 6 for me was like, you know, back when we carved on stones. But yeah, I told her, that's okay. We're gonna be doing everything on computers. I like to think I was right about that. But anyway, okay. For number 2, we've got, what's K stand for? Potassium. F stands for fluorine. So this is gonna be potassium fluoride. Okay, and for number 3, we've got hydrogen. Is hydrogen a metal or a non-metal? It's a metal, yeah. Okay, most of the time it acts as a metal. That's why it's over here. Okay, it might be a gas, but it behaves as a metal. Okay, in fact, it's the most metallic thing, right? So it is a metal. It donates the only electron it has. Then it has a full outer shell. None. No outer shell. And that's kind of weird, but okay, it does act as a metal. It does also act as a non-metal sometimes. Here's how you can tell whether it's acting as a metal or a non-metal. Metals are always listed first. So if hydrogen is first, it's a metal. If it's anything other than first, it's behaving as a non-metal. All right, so yeah, hydrogen is one of those weird ones. So this stuff is hydrogen iodide. Very cold, yeah. Okay, number 4, we got calcium with bromine. Does the 2 change what I do here? No, it doesn't. Not in an ionic compound. Okay, we never use prefixes in an ionic compound, right? There's only one way for calcium and bromine to go together, okay? Because calcium has a charge of +2 if you look on your periodic table. Okay, bromine has a charge of -1. Anytime these two go together, there have to be two bromines. So we never use prefixes in an ionic compound. So this is simply calcium bromide. If it has iron and it's more than one charge, then we have to put a Roman numeral, and we haven't got there yet. We will. Okay, number 5, we have Al, which is aluminum. We have At, which is astatine. Aluminum has a +3 charge. Astatine is a -1. That's why there's 3 of them here. Okay, remember the drop and swap? Okay, that's where that comes from. Okay, so we got that this is aluminum astatide. Now, the International Union of Chemistry and Applied Physics did actually a couple of years ago officially change the name of aluminum. It is now aluminium. I refuse to change. That just sounds wrong. I don't drink soda from an aluminium can. I do not drive an all aluminium F-150. I don't. Yeah, just it's not right. Okay, not right. Okay. The International Union of Physics and Applied Chemistry, IUPAC. They're the ones in charge of naming. Yeah. I don't know. I don't know. They were flexing their power. I have no idea. Apparently, it was originally pronounced that way, and it was Americanized after that. And well, we pronounced it wrong. All right, let's have a look at the rest of these. Okay, so for number 6, okay, we have cesium with sulfur. So this is going to be cesium sulfide. All right, we've got sodium with oxygen, so that's going to be sodium oxide. And again, remember, there's no prefixes in ionic compounds, so the numbers are irrelevant when it comes to the name. Okay, for number 8, we've got barium, and then it's selenium. So it can be selenamide or selenide. Either one is acceptable, okay, in terms of how you put the "ide" ending on selenium. Okay, selenide, selenamide, doesn't really matter. Okay, all right, for number 9, we've got radium and tellurium. Okay, so that's going to be radium telluride. All right, for number 10, we've got lithium with fluorine, so that's going to be lithium fluoride. Number 11, we've got rubidium with sulfur, so that'll be rubidium sulfide. And guys, I don't care whether you spell sulfur with an F or a PH. Either way, again, is acceptable. Okay, some people like the PH, some people like the F, whatever. Okay. Then for number 12 here, I've got strontium with iodine, so this will be strontium iodide. Okay, 13, we got calcium with oxygen, so that'll be calcium oxide. And lastly, we've got magnesium with selenium, so that'll be magnesium selenide. Okay, questions on any of those?